Welcome to Everyday Explained, your daily 20-minute dive into the fascinating hows and whys of the world around you. I'm your host, Chris, and I'm excited to help you discover something new. Let's get started.
You know that moment when you turn on the tap, expecting water to flow instantly?
Yeah, it's something we totally take for granted.
It really is. It's so reliable, especially when you compare it to uh, other utilities that might hiccup now and then, like the internet going down or maybe a power flicker.
Right.
What's the unsung hero ensuring that steady stream? Often it's that large, sometimes kind of quirky-looking structure you're probably seen around the water tower.
That's right. These elevated tanks, they just become part of the scenery, don't they? We barely even register them sometimes.
Exactly.
But for you to have that dependable flow of water, they play an absolutely vital role in our municipal water systems. So in this deep dive, we're going to really explore the inner workings of these, well, seemingly simple structures.
Okay.
Our goal is for you to understand the whole journey, really, from the initial water source all the way to when it reaches your home. We've pulled together, a variety of information to try and give you a full picture of how it all happens.
And what's immediately fascinating as you start digging into this is realizing it's not just about, like, storing water way up high. These towers are actually pulling off a triple feat.
Mm-hmm.
They're reservoirs, right? They're essential for maintaining pressure in the system, and they're even a critical backup.
Okay, so let's start at the beginning for folks. Where does the water in the water tower even come from?
Okay, yeah. The journey for your water begins with a source, and this could be a well drawing from groundwater, maybe a river flowing nearby, or a larger body of water like a lake or a reservoir.
Right.
We looked into the Nina Water Utility, for example. Their raw water is sourced from Lake Winnebago.
Okay, Lake Winnebago.
Now, as you can imagine, water straight from the environment isn't quite ready to drink. It needs to undergo a pretty significant transformation first.
Right, the purification process. So what exactly needs to happen to get it from the lake to, drinking quality?
Well, it's a multi-stage process, really. It's designed to make sure the water is both safe and pleasant for you to use.
Yeah.
Typically, this involves softening.
Softening. What's that do?
That removes dissolved minerals that can make water hard, build up on fixtures, that kind of thing.
Gotcha.
Then comes filtration, where sediment, tiny particles, and other impurities get removed. And finally, disinfection takes place often using chlorine, sometimes ozone, or UV light.
To kill the germs?
Exactly. To eliminate any harmful bacteria, viruses, or other pathogens. The end result is clean, germ-free water that meets all the safety standards for you and everyone else.
Okay, so now we've got this pristine water. How does it then make its way towards the water tower? It's not going to magically float uphill, is it?
Huh? No, definitely not. This is where powerful pumps come in. They're known as high-lift pumps.
High lift, okay.
These pumps are responsible for pressurizing the treated water and pushing it into the primary feeder pipes of the water distribution system. Think of these as the, major highways of the water network in your community.
Ah, the main arteries.
Precisely. And a water tower, well, it's connected to these main arteries. So the water flowing in those main pipes essentially has two paths it can take, right?
Mm-hmm.
It can keep going to meet immediate needs, homes, businesses,
Mm-hmm.
or it can divert upwards towards the tower.
Mm.
What determines which path the water takes? Is it like a valve opening and closing?
It's less about a conscious decision or a simple valve and more about the physics of pressure and flow within a closed system.
Okay.
When the rate at which the pumps are pushing treated water into the system is more than the amount of water that's currently being used by the community.
Like maybe overnight when fewer people are using water.
Exactly. During those low demand periods, that excess water, because the whole system is under pressure, will automatically flow into the water tower tank. It's essentially taking the path of, well, least resistance to an area of temporarily lower pressure, which the empty space at the top of the elevated tank kind of represents.
That makes sense. So the tower is essentially filling up during those times when overall water usage is lower than what the treatment plant is putting out. Okay, so now we've got a significant amount of water sitting way up high in this tank. What's the advantage of that elevation? It has to be more than just a place to store water, right?
Exactly. That height is absolutely crucial. By elevating the water, the tank is storing potential energy, in this case, gravitational potential energy.
Ah, physics class flashbacks.
Right. Think back. An object held higher has more potential to do work when it's released. With a water tower, that height translates directly into water pressure at ground level for you.
Ah, the pressure. We came across that in our research, something like 0.43 psi for every foot of height. Is that right?
You're spot on with that figure. For every foot the water is elevated, it exerts roughly 0.43 pounds per square inch of pressure.
Okay, 0.43 psi per foot. Why is that consistent pressure so important when you turn on your faucet or, take a shower?
Well, typical municipal water systems aim to maintain a pressure range of about 50 to 100 psi at your property. This pressure is vital for a couple of key reasons.
Okay.
First, obviously, it ensures that the water has enough force to travel through the pipes and reach your taps, even if you live on a higher floor or further away from the main lines.
Makes sense.
Second, and maybe less obvious, adequate pressure helps to prevent contaminants from potentially entering the water system. Think about leaks or backflow situations.
Right, you don't want stuff getting in.
Exactly. If the pressure inside the pipes is consistently higher than the pressure outside, it's much harder for pollutants or untreated water to get in and compromise your water quality. It's a fundamental part of safe delivery.
That makes perfect sense from a reliability and safety standpoint. So when we talk about these water towers, how much water are we typically talking about them holding? Are these neighborhood things or are they massive?
The size of a water tower's tank is generally designed to hold approximately 1 day's worth of water for the community it serves.
1 day's worth. Wow.
Yeah. This capacity allows the system to manage those fluctuations in demand we talked about, and importantly, it provides a vital reserve in case of, say, pump failures or power outages at the treatment plant.
Okay. So what's a typical size?
Well, smaller towers, maybe serving rural areas or smaller communities, might have a capacity around 250,000 gallons.
250,000 gallons.
Larger ones in more densely populated metropolitan areas can hold upwards of 1 million gallons, sometimes even more. It really depends on the population being served.
1 million gallons. How big is that? Can you give us some scale?
Sure. Think about a standard backyard swimming pool. That typically holds between maybe 20,000 and 30,000 gallons.
Okay.
So even a smaller 250,000 gallon water tower holds, what, maybe 10 swimming pools worth?
Yeah.
And the big ones, 40, 50 swimming pools up in the air. It's a truly substantial volume.
Wow. Picturing that much water held aloft really puts things in perspective. And it makes perfect sense how that stored volume helps smooth out the peaks and valleys of water usage throughout the day. So when everyone decides to water their lawns at like 6 p.m. on a hot summer evening, the tower can help compensate for that surge.
Precisely. The water stored in that elevated tank acts as a buffer. It's readily available to supplement the output of the treatment plant when demand is high, like those peak usage times you mentioned.
Right.
Then, during periods of lower demand, like overnight, the pumps can work to replenish the water in the tower, getting it ready for the next day's needs.
And the system also creates an economic advantage for the water utility, doesn't it? They don't have to build pumps big enough for the absolute craziest peak demand hour of the entire year.
Exactly right. That's a huge benefit. By having the storage capacity, the municipality can size their pumps based on the average daily demand rather than the much higher and often brief peak demand.
Which saves money upfront on equipment.
Right. Consider a scenario where peak demand might be, say, twice the average. Without a water tower, they'd need pumps with twice the capacity. That means significantly higher initial capital costs.
And running costs too, I bet.
And increased energy consumption throughout the year, even when that extra capacity isn't needed most of the time. The tower allows for a much more efficient and cost-effective operation, which ultimately benefits consumers through, hopefully, lower utility costs.
We also learned that water towers play a critical role in firefighting efforts. How does having that elevated water supply specifically help in an emergency like that?
That's incredibly important. During a fire, the demand for water can just skyrocket in a very short period. Firefighters need substantial pressure and a high volume of water to effectively fight flames.
Right, the big hoses need a lot of flow.
Absolutely. A water tower ensures that there is a readily available supply of water at a reliable pressure, even if the pumps at the treatment plant are struggling to keep up with that extreme demand, or maybe if there's a power outage affecting those pumps.
So it's a crucial backup.
It really is. Historically, before we had modern pressurized water systems with elevated storage, big urban fires could be absolutely devastating. Water towers provide that critical backup and sustained pressure needed for effective firefighting. It's a direct contribution to public safety.
Okay, so the water isn't just sitting stagnant up there in the tower, is it? What's done to maintain the water quality while it's stored?
That's a really important question. You don't want water sitting still for too long. To ensure it remains fresh and high quality, most modern tanks are equipped with mixers.
Mixers, like in a giant cocktail shaker.
Sort of, but much slower and gentler. These devices circulate the water within the tank. This helps maintain a consistent level of disinfectant, like chlorine, throughout the whole volume.
So it keeps the chlorine mixed in evenly.
Exactly. It prevents the growth of any waterborne pathogens and ensures the water reaching your home stays safe. The mixing also has the added benefit of helping to prevent the water from freezing in colder climates.
Freezing in that huge tank.
Oh, yeah. There's actually a pretty amusing story from the Nino Water Utilities past, apparently before they had these modern mixers,
Oh.
where they found icebergs as big as Volkswagens forming inside the towers during particularly cold winters.
Get out. VW-sized icebergs in the water tower.
That's the story. So, yeah, maintaining movement is key for water quality and preventing massive ice blocks.
Gigantic icebergs in your drinking water, definitely not ideal. And I imagine these towers require regular maintenance and upkeep, too. It's not just build it and forget it.
Absolutely not. Regular maintenance is essential. You need to ensure the structural integrity of the tower itself and, of course, the continued quality of the water supply.
What does that involve?
Well, regulations vary, but for example, the Wisconsin DNR mandates thorough inspections every 5 years. Sometimes these can be done using submersible robots while the tank is full.
Cool, water robots.
Yeah. But typically, every other inspection, so maybe every 10 years, requires the tower to be completely drained.
Drained, the whole thing.
The whole thing. So a detailed internal examination can be performed. This is the time to conduct any needed repairs, maybe dealing with corrosion, structural issues, that sort of thing, and also to remove any sediment that might have built up at the bottom over time.
Makes sense.
Then, once the inspection and any maintenance are done, the tower has to be carefully disinfected before it's refilled and put back into service. It's a whole process to ensure it's clean and reliable.
Okay, so the water has been sourced, treated, pumped up, stored safely, maybe mixed a bit. Now, how does it finally make its way from that elevated tank back down to my house when I turn on the faucet?
This is where the elegance of gravity comes full circle.
Back to gravity again.
Yep. When the community's overall water demand exceeds the rate the pumps are currently pushing water in.
Like during that morning shower rush.
Exactly. The water naturally flows out of the elevated tank due to gravity. That potential energy we talked about earlier, the energy stored by the water's height, is now converted into kinetic energy.
The energy of motion.
Right, the energy of the water moving. And this pressure, generated purely by the weight of the water column in the tower, propels the water through that whole network of distribution pipes, ultimately reaching homes and businesses with the pressure people expect.
It's almost like having a giant citywide plumbing system powered mostly by gravity once the water's up there. One of our sources mentioned thinking of the whole system as a virtual ocean, with the water level in the tower representing the surface. Can you expand on that? That sounds interesting.
Certainly, it's a helpful analogy. Imagine the entire underground network of water pipes in your city as a kind of, well, subterranean ocean.
Okay.
The water level in the elevated storage tanks acts as the surface level of this virtual ocean.
Right.
Now, just like in a real ocean, the deeper you go, or in this case, the lower your elevation in the city relative to the water tower, the greater the water pressure will be.
Oh, because there's more water above you.
Yeah.
Pushing down.
Exactly. Conversely, the higher your elevation, the closer you are to that surface, and the lower the pressure will naturally be. This analogy helps visualize why ensuring consistent pressure for everyone can be a challenge, especially in hilly areas.
And that's why you sometimes see different pressure zones established in cities with big hills or significant elevation changes. Each zone might have its own tower.
Precisely. In cities with considerable variations in topography, relying on just one water tower to provide adequate pressure everywhere can be impractical. You'd either have too much pressure down low or not enough up high.
Right.
So many larger or hillier cities are divided into distinct pressure zones. Each zone is often served by its own dedicated water tower or elevated storage, acting as the surface for that specific area. This allows for much better management of water pressure within each zone.
So everyone gets like a reasonable pressure range.
That's the goal, yes.
Okay.
Ensuring everyone receives water at an appropriate pressure, regardless of their elevation.
That makes sense.
Yeah.
What about those really tall buildings you see in major cities? They create their own huge elevation changes just within one building. How do they get water up to the top floors with enough pressure, like someone on the 50th floor?
Good question. Tall buildings often incorporate their own internal water distribution systems to handle exactly that.
So they don't just rely on the city pressure.
Well, The city pressure might be fine for the lower floors, but as you go higher and higher in the building, the pressure naturally drops off, just like climbing a hill relative to the city's water tower.
Right. Same principle.
So to compensate, most skyscrapers and other very tall structures are equipped with their own booster pumps. These pumps take the incoming city water supply and increase the pressure needed to serve the upper floors adequately.
Okay, so internal pumps.
And often, especially in places like New York City, you'll see those iconic wooden tanks on the rooftops.
Yeah.
Hmm.
Always wondered about those.
Those are essentially mini water towers for the building itself. They act as elevated storage, providing a local reserve and helping maintain consistent pressure throughout the upper levels of that specific building.
Huh. So the city has its big towers, and tall buildings can have their own little ones on top. Fascinating.
It's a system within a system sometimes.
So are these big public water towers absolutely essential for every municipal water system? Are there places that get by without them?
While water towers offer huge advantages, reliability, pressure regulation, energy efficiency, they aren't universally indispensable.
No.
Some regions, maybe those lucky enough to have a water source at a naturally high elevation, like up in the mountains,
Right.
they can use gravity directly to distribute water across their service area, minimizing the need for big elevated storage tanks.
So gravity does all the work from the start.
Pretty much. Additionally, in certain situations, a water system might rely solely on a network of pumps to maintain pressure and meet demand constantly.
Just pumps, no tower.
It's possible. But those pump-only systems are typically more complex, definitely more energy intensive because the pumps have to react instantly to every change in demand, and they generally offer less resilience if there's a power outage or pump failure. There's no buffer.
Yeah, that backup seems really important.
It is. So for the majority of public water supplies, especially in areas without dramatic natural elevation changes, elevated storage, the water tower remains a highly effective and dependable solution.
So to bring it all together for you, the listener, these seemingly simple water towers are doing, what, three main things?
That's a good way to summarize it.
Okay, first, they store water to help smooth out the daily ups and downs in demand that we all create.
Yep, demand leveling.
Second, they use gravity, that free energy source, to maintain consistent water pressure so it flows reliably from your taps and also helps keep the system safe from contamination.
Pressure maintenance and safety.
And third, they provide a crucial backup water supply for the community in emergencies, like power outages or big fires.
Emergency backup. Exactly. Storage, pressure, backup.
It's really quite remarkable how such a, straightforward-looking structure addresses some pretty complex challenges.
They truly are a testament to some clever practical engineering, providing a vital service that, thankfully, most of us don't even have to think about day to day.
Okay, here's something to consider for you, our listener. The next time you happen to drive past a water tower, or maybe you can see one from your window, take a moment to really appreciate it.
Yeah, give it a nod.
Seriously.
Yeah.
It's more than just a landmark on the horizon. It's this vital piece of infrastructure quietly working 24/7 to ensure you have access to one of life's most fundamental necessities, reliably and safely. Think about that intricate balance of water supply and demand it manages, the clever use of potential energy just through height, and the crucial role it plays in public safety, all embodied in that, well, often overlooked structure.
Well said.
Maybe even take a moment later to look up some unique water towers online. You mentioned the Brooks ketchup bottle earlier. Didn't we see that? Or those NYC rooftop tanks? Or just research the history of water towers in your own community. It's a deeper story than you might initially think.
And that wraps up today's episode of Everyday Explained. We love making sense of the world around you 5 days a week. If you enjoyed today's deep dive, consider subscribing so you don't miss out on our next discovery. I'm Chris, and I'll catch you in the next one.